Okay, this is January 2024 paper, Unit 3. Question number 1 is this question is about the hormone testosterone, the structure of which is shown. Give the name of each of the three circled functional group. So of course this is going to be alcohol, okay, and this is alkene and this is ketone, right? So functional group 1 is ketone, functional group 2 is alkene, functional group 3 is alcohol. And we know there are three types of alcohols. We have primary alcohol, then we have secondary alcohol, then we have tertiary alcohol. They are not asking the type of alcohol, they are only asking to identify the functional group. So if you have OH, so that's going to be alcohol, and that's it. Part B says describe a chemical test and the expected positive result for both functional group 2 and functional group 3. Functional group 2 is alkene, okay, and functional group 3 is alcohol. So they are saying, what's the test for the functional group 2? Of course, we will add bromine water. We will add bromine water, isn't it? So after adding bromine water, so we know that the color of bromine water is orange. And as a result of this, after the reaction, when the bromine will be added to the double bonded alkene, so it's going to be colorless. So orange to colorless, or I can say bromine decolorizes. If you can see, the color of the bromine will be changing. So it's mean it has reacted with alkene. So that shows the presence of alkene. Then what's the test for functional group 3? That's an alcohol. That's an alcohol. So, alcohol reacts with PCl5. When you will react this alcohol with PCl5, HCl would be formed. HCl would be formed. And as a result of this, we will see misty fumes. We will see white fumes. Okay, we will see white misty fumes, steamy fumes, right? So if you can see misty fumes after reacting PCl5 with OH, it shows that it shows the presence of OH group. And then in a mass spectrometer, the molecular ion formed can break apart into smaller fragments. One way the molecular ion can fragment is shown by the dashed line, like this one. This is the fragment. This dashed line has divided this molecule into two categories. This is your first fragment and this is your second fragment. Okay. What they are asking in this one, they are saying deduce the mass to charge ratio of the fragment shown by the unshaded area, assuming it forms a singly charged ion. Okay. So I can say unshaded area is this one. I have to count the total number of atoms in it. So if you can see 1, 2, 3, 4, 5, 6 carbon atom, I have 6 carbon atom, then you have to count hydrogen atoms. It has 3, it has 2, then 1. So how many hydrogens we have? 8 hydrogens we have. And how many oxygen I have? Only one oxygen. Okay. So, and they are asking mass to charge ratio. So from the periodic table, when you will see the atomic masses, so carbon is 12 times 6, hydrogen is 1 times 8, and oxygen is 16. So you will see it would be 96. Okay. And they are saying the overall charge is plus 1. They are saying the overall charge is plus 1. So 96 over 1 is 96. So that's the mass to charge ratio of the fragment. Okay, easy. When molecular ions fragment, they form a smaller ion and another type of particle. State the other type of particle formed, that's going to be the radical. You know why? Whenever you have any of the molecule, we know that we have learned in the theory of mass spectrometry that in a mass spectrometer, only cations are determined, isn't it? We cannot determine anion by using the mass spectrometry. We cannot determine the neutral atom, neutral molecule, neutral compound by the mass spectrometry. Only remember the cations are determined. Only the cations. So when high energetic electrons are bombarded on a molecule, the molecule will be broken down into two different categories. The first one would be the radical, that is not determined in a mass spectrometer because this is not a cation. Only the cations are determined. This is your cation, so this would be, you can say, determined by the detector. Simple. So they're asking other type of particle form. Of course, that's going to be the radical. That's going to be the radical. Okay. Question number two, an experiment was carried out to determine the concentration of citric acid in a lemon juice using a titration. Or three students use the following procedure. Procedure one, step one, add this much grams of lemon juice to 250 centimeter cube volumetric flask. Okay. Make up the volume of the lemon juice to 250 centimeter cube using deionized water and mix thoroughly, and then pipette 25 cm cube of the diluted lemon juice into a conical flask and add a few drops of phenolphthalein indicator. Titrate the diluted lemon juice with standardized sodium. Standardized sodium hydroxide means whose concentration is known. That is 0.103. Student A obtained the results shown. Draw a circle around the concordant results in the table. Of course, what are the concordant results? When the difference in the two values is minimum, around zero point 0.1 or zero point 0.2. That's going to be your concordant reading. So they are quite closer to each other. So that's the concordant readings. Okay. And then calculate the mean titer using your answer from A. Of course, mean means sum of the values divided by the total values. So I have sum it up and then divided by the 2. So I got 24.25 centimeter cube. The equation for the reaction between citric acid and NaOH is shown. Okay, this is an acid-base reaction. State the color change. We have used phenolphthalein. Phenolphthalein is pink in base and phenolphthalein is colorless in acid. So we have to see whether the color will be changing from colorless to pink or pink to colorless. Remember, that is very important. So we have to see what is present in a conical flask. What is present in a conical flask? Okay, so titrate the diluted lemon juice. Lemon juice means this is present in your conical flask, and NaOH is present in the burette. NaOH is present in the burette. Okay, so when I have conical flask, okay, and in the conical flask, I have a lemon juice. When I will add phenolphthalein into it, so that's going to be colorless. When you will add NaOH from the burette, so the colorless will be changing into pink. Okay, simple. Or calculate the percentage by mass of citric acid in the lemon juice using your mean titer from B and give your answer to two significant figures. So remember, we have to find out the percentage by mass of citric acid. You know what's the concept to find the percentage by mass? Whenever we are going to find out the percentage by mass, remember, let's say, I'm saying you have to find out the percentage by mass of sodium in sodium carbonate. So what we used to do, mass of sodium divided by total multiplied by 100, right? So they are asking to find out the percentage by mass of citric acid. So we have to find out the mass of citric acid divided by the total mass, divided by the total mass. I think they have given the total mass. Let me see. Yeah, they have given you the total mass of lemon juice, that is 24 grams. So what we are supposed to do, we have to find out the mass of citric acid and then divided by the total mass, that is 24, and then multiplied by 100. It would give you the percentage by mass of citric acid. But this is of 5 marks. How can I find out the mass of citric acid? Number one, First of all, we have to find out the mole of NaOH. For the mole of NaOH, they have given you the concentration of NaOH, that is 0.103. So I put 0.103 multiplied by the volume of NaOH, that was this one, 24.25. Okay. And I got the moles of NaOH. I got the moles of NaOH, right? Mole of NaOH. And then I'm supposed to use I'm supposed to use more significant figures to get the accurate value, right? Okay. So I'm supposed to write 2.49. I'm supposed to write 2.4978 times 10 to the power minus 3. That more accurate value. That's the mole of NaOH. And then we have given equation. That is this one. The mole ratio between citric acid and NaOH is 1 is to 3. If I want to find out the mole of citric acid, so the ratio is 1 is to 3. So let's say, let me show the working why I have divided this by 3. This is your citric acid, right? And this is NaOH. The mole ratio is 1 is to 3. I know I have to find out the mole of citric acid, and the mole of NaOH is 2.4978 times 10 to the power minus 3. So that's why I have divided this by 3. When I would divide it by 3, so getting I would be getting the mole of citric acid, that is going to be 8.32. Let me 8.3258 times 10 to the power minus 4. This is the mole in 25 centimeter cube. You know how? As you can see, they are saying I am taking 25 centimeter cube of the diluted lemon juice from 25 centimeter cube to 250 centimeter cube for the titration. So of course, when I would be finding out the moles, that's going to be in 25 centimeter cube. If I have this much moles in 25 centimeter cube, so how much moles would be there if I have this much volume? So you are supposed to cross multiply this and you would be getting the moles of citric acid that is present in 250, that is present in 250 centimeter cube. So the answer is going to be so the answer is going to be the same. So the answer is going to be the same, but it would be 10 raised to the power. It would be 10 raised to the power minus 3, not 4. Then I got the mole of citric acid. I'm going to find out the mass of citric acid. Mass is equal to Mr. Moles. I know the MR from the periodic table. That is 192. You can find it out. Okay, they have given that is 192. So multiplied by the moles. Multiplied by the mole. So the mole is this one. So the mole. Okay. So when you will be multiplying this by 192, so you would be getting 1.59, 1.5986 up to four significant figures. 1.9559 and then 86. This is the mass of citric acid. To find out the percentage by mass, I'm going to divide it by the total mass that is given in the question, that is 24.0. Okay. So you would be getting the final answer. So the final percentage is uh, let's let's do this 1.5986 divided by 24. It would give you it would give you 6.7%. Okay, that's the answer. Simple, easy. So the concept is that when you're going to find out the percentage by mass of anything, so you need the mass divided by the total mass and then multiplied by 100. Okay. And then, uh, yes, two other students, B and C, also followed the procedure to find the concentration of citric acid in similar samples of lemon juice. Student B added too much deionized water in step 2. State how student B should correct this mistake. So remember, in step 2, what's going on in step 2? What's going on in step 2? Make up the volume of the lemon juice. Okay, okay. Normally, when we make a syrup, especially antibiotic, so what we do, we have to make up the solution. We have to add water. What if I have added, by mistake, I have added more water? Like they have marked in a bottle, okay, but by mistake, I have added too much water. So what's the solution now? What I'm supposed to do? So you know what to do? Just discard the solution. Just discard the solution and then make the new solution. That's it. Okay. Otherwise, we can't do anything. We can't do anything. Remember, we can't do anything. Okay. So they are saying what I have written: discard the solution, then rinse the flask, and then make a new diluted solution. Without doing this, there is no any other solution because it's diluted. If you are thinking, sir, just pour the water into any other container, we can do this. But initially, the solution is diluted and we can't do anything. Okay. We have skipped this part. In a D, they are saying suggest a possible reason why the value obtained in C is valid, even though lemon juice also contains some ascorbic acid and a malic acid as well. So in C, we got much percent, right? So suggest a possible reason why the value obtained in C is valid. Okay. So basically, tighter value, tighter value will be having minor effect because in lemon juice, malic acid and ascorbic acid are present in a little quantity. They are present, but they are present in a little quantity. So you can say uh, negligible quantity. So titer value will be having a very minor effect, very minor effect. Like when we are going to do titration. So if these acids are present, of course, it would affect your neutralization point because we are neutralizing it with sodium hydroxide. But they are saying uh, they are present in a very little quantity. So if they are present in a very little quantity, let's say if I have 1 mole of citric acid, so the presence of malic acid and ascorbic acid would be 0.00000001 mole. So if you are going to titrate it, so the result would be different, but there would be a minor effect. Okay. So they were saying suggest a possible reason why the value obtained in C, why the value obtained in C is valid, even though lemon juice also contains some ascorbic. So why this is valid? Because they are present in a very little quantity. That's it. And then into student C used sodium hydroxide solution labeled 0.103 mole per dm cube that had been made up several months ago and stored since then. Explain what effect this would have on the mean titer compared to student A. When you are going to make up a solution and you are going to just keep for a long time, so you know what would happen? Sodium hydroxide react with carbon dioxide because sodium hydroxide is a base, carbon dioxide is acidic. Non-metals non-metals oxides are acidic in nature. They will do reaction and they will form sodium carbonate. So mean titer will be higher since sodium hydroxide becomes diluted. So if you are going to titrate something else, so you need more volume of NaOH. You need more volume of NaOH. That's why I'm saying that the mean titer value will be higher. Okay.